Hello everybody, my name is Vikas Vinayaka and today I'll be presenting on operation of DIMMs using DDR4. First, a little bit of outline. Initially I'll go through the computer memory organization and then I'll briefly explain the DDR interface, and then we'll talk about the DDR4 advantages and techniques, and then I'll talk about the types of DIMMs which are available and the future of memory technologies. So here are some memory technologies as a refresher. So DDR stands for double data rate, as we all know, and so it means that the data is sent in the rising as well as falling edge of the clock. And SDRAM stands for synchronous DRAM. So SDRAMs, so data is sent with respect to the clock, so it's not asynchronous. And the advantage of SDRAMs over asynchronous DRAMs is that it makes it faster because it can be interleaved using multiple banks of memory. And a memory bank is defined as a collection of small DRAM arrays. So in a DRAM chip, the entire memory cells is not one huge array. It is split into multiple banks. So this helps in speeding up of the data reading and writing. And so memory is configured as X4 or X8 parts, or it can be any other number. So that means that when there is a read command which is given to the chip, there are that many bits or words which are written which are read out from the chip. So for a 4-bit part, there are X4 part, there are 4 bits which are read out at once. So before we dive into the DRAM specifics, I want to explain the computer memory organization and where it is used. So on the left here we have a block diagram of a typical computer. We have the CPU and the north bridge and the south bridge. These two together they form what is called as a chipset. And the north bridge connects to the CPU using the front side bus, which is a very high speed bus. And the north bridge usually handles all the high speed interfaces such as the RAM interface and the graphics interface. The south bridge is considered as it's also called the I/O hub controller, and it interfaces all the low speed interfaces such as USB, SATA, and Ethernet, and such things. The RAM is usually used as a SDRAM DIMMs. DIMM is a dual inline memory module, which I'll explain more in the next slide. So on the right here we have a motherboard, which is a physical computer. Below the fan here is the CPU, and below this the heatsink is the chipset. And here we can see the DIMMs. So this is a DIMM module. The computer RAM is typically a DRAM, and it has gone through many packaging styles. Initially we used to have discrete DRAM memory chips, and they used to be soldered directly onto the motherboard itself. And the disadvantage of that is they were not upgradable, so you cannot, as newer memory technologies arrive, you cannot change them. So that was rectified using SIMMs, which is single inline memory modules. The idea here is the DRAM chips are soldered onto a PCB, and that PCB is plugged into the motherboard connector. But the disadvantage here was it had only 32-bit data bus, but the newer processors had 64 bits, so it was not compatible with that, and 2 SIMM modules would have to be used together to get 64 bits. So to solve that, we came up with DIMMs, which is dual inline memory module, which is used even today. And here the idea is the idea is the same, where the DRAM chips are soldered onto a board and that is plugged into the motherboard. So here is a basic DRAM, SDRAM DDR interface. So there is a CPU which actually connects to the memory controller, and usually the memory controller is integrated into the CPU itself, and the memory controller connects to the DDR SDRAM using four main signal paths. We have the DQ, the DQS address, and CK. DQ is a bidirectional bus which transfers the data in and out of the memory, and DQS is a clock which is given from the DDR SDRAM to the memory controller, and that will be synchronous with the DQ when the DDR SDRAM when the data is being read from the SDRAM, and the address is from memory controller to the SDRAM, which indicates what is the address at which the data is being read, and CK is the clock from the memory controller when the data is being written into the SDRAM. So why do we need to move to DDR4? There is always an never-ending demand for higher speed and lower power, and DDR4 achieves both. So it achieves lower speed by it achieves lower power by lowering the supply voltage from 1.5 volts to 1.2 volts in case of DDR3 to DDR4. And it also has higher transfer speeds by using many techniques which I'll explain later. And it also has higher module density because it supports up to 512 gigabytes per DIMM slot compared to 128 gigabytes in case of DDR3. Comparing the different DDR generations, we can see that the supply voltage is reducing in the newer generations, and DDR4 goes up to 3.2 giga transfers per second, and it has a prefetch of 8 bits. I'll explain more about this later. And it has the interface standard is called POD12 compared to the SSTL15 of DDR3, and I'll explain more about this later. Comparing the physical module differences between the generations, we can see that all the DDR generation DIMMs typically look the same except for the notch placements. So this is done so that the wrong kind of module cannot be plugged into a wrong socket. And DDR4 has one extra feature, which is it has a curved edge on the bottom, which helps in reducing the stress when it is being plugged into a socket. Briefly, the DDR4 speed rates, it goes from 1600 megatransfers per second up to 3200 megatransfers per second, as I said before. And here is the DDR4 command set. So here, this is all the instructions a DDR SDRAM chip needs in order to do the functions. So these are the commands which the memory controller sends to the SDRAM. The main ones are the activate, the read, write, and precharge. So activate opens a row using the address which is given here, and the read and write commands will do the respective thing. It reads or writes, and the precharge will precharge the bit lines to the so that it makes it ready for reading or writing. So how does DDR4 achieve such high speeds compared to DDR3? There are a couple of techniques. Firstly, the prefetch or the burst length, and it also has bank groups, and it has smaller row sizes compared to DDR3, which eases the bank switching. Oops. So firstly, prefetch. So this is a graph of the orange graph here shows the internal core memory clock compared to the different DDR generations. We can see that it doesn't change much, but the purple graph here shows that it is the total transfer rate from the memory is increasing. But how is that possible? I mean, it has to be ideally the same, right? But that is where the prefetch comes in. Prefetch is a technique where for a given read signal, it fetches multiple points of data. So it shoots out the data in a burst. That is called the burst length. So in DDR3 the prefetch was 8. In DDR2 the prefetch was 4. In DDR4 the prefetch number is still 8, but it has bank groups, which again increases the data rate. So here is a waveform of prefetch. Here is the clock coming in, and this is the read command. And we have something called the cast latency, which is the distance, the time taken from a read command up to whenever the first data comes out. That is called the cast latency. So here, the point from here to here is the cast latency. So as soon as this command comes in, there are 8 data words which are read out, and it is sent out as a burst. That is called the burst length, which is also 8. In terms of bank groups, I mentioned earlier that DDR4 has bank groups. So if the data is being read in a bank group, then if it is prefetched from a bank group, then it is slower. If it is prefetched from different bank groups, it is faster. So there is something there is an interleaving happening between the bank groups. So if one data is here and the other data is in a different bank group, then the time taken is much smaller, and so that will give a higher data rate. One thing we can observe here is the memory array speed is almost the same across the different generations. So that is not changing. So it's about 100 to 150 megahertz here, and in the DDR4 it is 100 to 266 megahertz. So the core clock is not changing. This is a timing diagram for DDR4 prefetch. Here we can observe the different bank group lines. For 4 bank groups, we have 4 lines here: bank group 0, 1, 2, and 3. So if the data is read from different bank groups, the latency is only TCCD-S, which is only 4. But if it is within a bank group, it is TCCD-L, which is 5 cycles. So how does DDR4 achieve lower power? So there are a couple techniques for that. Firstly, the reduction in the VDD, so that will directly correlate with the reduction in power for the same amount of current. And it uses the I/O standard called BOD12, which I'll explain later. It is called pseudo open drain at 1.2 volts. It also uses DBI, which is data bus inversion, and it uses smaller row sizes, which reduces the amount of current used for parasitic charging and discharging. So what is POD12? POD12 is a protocol standard for driving the output lines in a DDR4 SDRAM. On the left here we have the DDR3, which is a push-pull architecture, which is the standard is called SSTL. Here there is a termination on the receiving end, because the PCB lines here needs to be treated as transmission lines because the speed is very high. So there should be a termination on the receiving end, and when the output is high or the output is low, there is a DC current from the receiving side to the transmitting side. But that DC current doesn't happen in when the output is high in POD12. In DDR4, there is only a termination to VDD, not to ground. So there is a DC current only when the output is low here. When the output is high, there is no DC current. So that's how it saves power. The other technique is called DBI, which is data bus inversion. In POD 12, we saw that when the output is low, it doesn't draw, it draws current only when the output is low, not when the output is high. So in using DBI, it ensures that the number of zeros sent out is not more than 4. If we send out more zeros, there is more power wasted, right? So what this does is there is a counter here which checks for the number of zeros, and if the number of zeros is more than 4, it inverts the output. The entire byte is inverted from the memory cell here, and it asserts a signal called DPI. Okay, so there is inverted data on the output DQ, and DBI is asserted, which means the data has been inverted, and the same has to be reversed back at the receiving side. So this also saves a lot of power. So this is a DDR4 SDRAM chip block diagram. This is a Micron 512 megabyte SDRAM IC. It has 18 bits of address input, and it has inputs for bank group selection and bank selection. It has the row decoders here, and the row latches, and the column decoders and column latches. And there is this global I/O gating line, which connects all the all the bank groups. And there are local I/O lines in between the bank groups itself. Okay. And here we can see the clock. It's very small. So here is the input clock, and it goes through the DLL as we saw before, and this helps for aligning the DQS with the DQ. This SDRAM chip needs 3 supply voltages. One is VDD, which is the I/O supply voltage of 1.2 volts, and VDDQ, the core memory supply voltage of 1.2 volts, and the word line supply voltage, which is VPP of 2.5 volts. This is used for driving the word lines, as we have studied. It has to be a higher voltage to overcome the body effect. To transmit the high-speed data signals from the SDRAM, it has to go through the PCB lines, right? It has to go through PCB traces. But the PCB, the speed through which the signal propagates in a PCB is around 2 inches per nanosecond. So that means our input frequency is the period of the clock is much lower than the propagation delay. So there are multiple edges, multiple periods in the same length. Okay, that means that it has to be considered as a transmission line. Okay. So this is a typical PCB transmission line. It's called a microstrip transmission line, and for DDR4, its target impedance, characteristic impedance of that line has to be from 100 ohms to 120 ohms. It has to be designed for that. So for the DQ signals to be read out properly on the receiving end, it has to be aligned with the DQS lines. Okay, so that means the DQ and DQS have to arrive at the receiving end at the same time. So for that, we do something called PCB trace length matching. This is the unmatched traces here on the left side, and if that is matched, this is how matching is done for PCB traces. And this diagram shows typical DDR4 DIMM PCB. On the here we can see the DRAM chips, which are highlighted in the red colored rectangles, and it's 8-layer PCB. It has 8 SDRAM chips, and the chips are of FPGA footprint, which is fine pitch ball grid array. And here is a picture of the IC, and there are solder balls on the bottom, which are soldered onto the DIMM. And we can see the card edge connector on the bottom edge of the PCB. Moving to the types of DDR4 DIMM modules, they are categorized according to uh, different features and different types, as well as their physical sizes. Okay. Um, so this is one type of DIMM called UDIMM, which is unregistered DIMM. This is the simplest one, and it just contains DRAM chips on the board, and the output of DRAM chips directly connects to the memory controller. All the DIMMs have sorry, all the DIMMs have another small chip on board, which is called a SPD-ROM. It's a small E-square ROM which contains information about the DIMMs, like its size, the speed, etc. And this is read by the CPU during power on self test in order to know what kind of RAM is present in the system. The next is the registered DIMM. It contains an IC called RCD, a registering clock driver. So this buffers the command and address lines. It doesn't directly go to the DRAM chips. So this helps in increasing the reliability and makes it more robust. And these kind of DIMMs are mainly used in servers. Next is LRDIMM, which is a load-reduced version where not just the address and command lines, even the data lines are buffered. So this reduces the load on the data bus, which helps in adding more number of DIMMs on a board. This is again used in servers. The FVDIMM, which is fully buffered version, but this is very different from the past two DIMMs, where there is an onboard logic on the DIMM here, which converts parallel data from DRAM chips onto serial data, and that is sent serially to the memory controller. So this trades off the latency and speed in order to get massive capacity. This is again used in servers. So the last type is called NVDIMM, which is non-volatile DIMM. DIMMs, there is no rule that DIMMs have to have only SDRAMs on them. They can have other types of memory too. So here, this uses there is a JEDEC standard for a NAND-backed DRAM, where there are SDRAM chips as well as NAND flash on the same board. So it functions as a normal SDRAM DIMM, but as soon as there is a power failure, all the SDRAM contents are backed up to a NAND flash. So in order to do that, there is an onboard backup power in like it is stored in supercapacitors, and this is again used in servers. So categorizing it as in terms of sizes, there are mainly four types. The UDIMM, which we saw, is the biggest one, and then there is SODIMM, which is small outline DIMM, which are used in laptops or wherever it has to sit flat on the board. And then there is VLP DIMMs, which are very low profile DIMMs. These are used in blade servers. And then there is mini DIMMs, which are mainly used in embedded applications. So how do we implement a DDR4 DIMM system? Well, it's all about the standards. JEDEC has standards for almost all aspects of DDR4 system design. So here there is a list of standards here. So it dictates almost every aspect of it. And then there are ad hoc standards created by the companies themselves, like the DFI, which is DDR5 interface, which are used to make sure there is interoperability between different PHYs made by different companies. Just a brief mention of other types of DDR memories. There is GDDR, which is graphics DDR. It is this type of memory is soldered on the board next to graphics processors. And then there is LPDDR, which is low power DDR, also called mobile DDR memories. And these are used as a package on package. They are soldered on the along with the processor itself. It is used in mobile devices. So what the future holds for memories, DDR4 memory is the most cutting edge type available right now. The next version is DDR5, and its development is in progress. The specification is being finalized by JEDEC, and it will be supposed to be released in 2018, and devices to be available in 2020. Micron is working on a hybrid memory cube which uses stacked DRAM chips connected by through silicon vias. There are other cutting edge technologies like 3D crosspoint by Intel, and there is phase change RAM, resistive RAM, etc. So that's all I have. I can take questions now. These are the references, and I can take questions now. Thank you.
Our speaker. I have high hopes someone's going to ask questions besides me.
Oh, through silicon vias. Through silicon vias. So they, yeah, TSV through silicon vias.
So what kind of DIMM is used for DDR4?
Oh, DDR4 uses all kinds of DIMMs.
Really? So go back
Yes.
to your listing of DIMMs. Okay, does it use an unbuffered DIMM?
Yeah, unbuffered DIMM
What?
is. Yes, I mean it connects.
DDR4 operates fast. So if you're going to operate fast, is it possible to use no buffering?
I looked at the JEDEC design, the reference design, and in the schematic it doesn't. The DRAM chips directly connect to the card edge connector. Actually,
Okay, let's
so
pull up a web browser. There's each one of these, yeah, go to Google there, and then, yep, and then type DDR4 DIMM. And let's go look at, let's look at that middle one. It looks like an unbuffered, the second one from the left. You're gonna put, oh.
yeah.
Unbuffered DIMM, clock unbuffered DIMM,
Yeah, so
non-ECC. Can you zoom in on the picture? Not really, listen what I meant. I was clicking to show what the DIMMs are, because I don't think those are, it says DDR4, but those chips don't look like DDR4 chips.
oh, how can you
You don't think they look like it?
how can you save just by looking at them?
How can I say? Because I've looked at lots of DDR4 chips.
That's
what
the
is-
brand trying.
That's a what?
The brand Crucial tries Ulas or something.
They don't what?
Trying full. Yeah. No, they don't.
Oh, I don't know why it says DDR4. So I got another question then.
Yeah.
Actually, I got a question. How much did that cost?
Oh, it's about $100.
What is it?
I checked in Amazon. It was like $100.
$62.
Oh yeah, 62. Yeah.
All right, next question. How many bits do you get out of a DIMM in a read or a write?
There are 64 bits. You mean per second?
Yeah, no, I mean, when you write or read from the DIMM, how many bits do you get out?
It actually depends on which DRAM has the data. So that corresponding chip would give the data.
So you said at the beginning that the DRAM chips, they were by 8,
Right.
right? Now go back to the figure we were just at, the one on the web page. See that lower, go to the middle, see where it says 1020? No? Go to the right a little, see where it says 1024?
64.
Yeah.
So that's 64 bits input out. How can you tell that by looking at the DIMM?
Oh, the
Turn on
DD.
DIMM again. How can you tell it's 64?
The DDR4 standard is DD64 bits output. The standard defines that.
You can tell it's 64 because there's 8 memory chips, but it's more common
Okay.
to use 9 or 72 bits
Okay.
because when you are writing and reading high speed, you have a check bit for error correction. So
Yeah.
you see the comment says no, non-ECC
Non-ECC.
there on the
Yeah,
right?
yeah.
There's no error correction. Can we hit the back arrow on this? I don't know why, I've never heard of a product that used unbuffered DDR4. That just seems ridiculous to me. But go to, let's see. Go to the, these look good.
Wikipedia?
Yeah, go ahead, click on that. Okay, so look at that first image, click on the first image. What kind of DIMM is that?
This is unbuffered.
That's unbuffered?
Yeah, because buffered would have additional chips on the bottom.
Yeah, so those chips on the bottom there, the registers, the load reduced DIMM?
Oh, these are, I think these are termination resistors, right?
They're what?
Termination resistors?
Oh, they
These-
are, okay.
Yeah.
I can't see it that well.
Yeah.
I thought the termination resistors were like the gray and silver, and then the ones in between were chips. Like that's a chip. The ones
No,
on the
that
right
is
the resistor.
that is a resistor network.
What's that?
It's a resistor network. It has 4 resistors inside. Like it has. It's a single package which has 4 resistors on.
Oh, is it? Okay.
Yeah.
Go back and get that. Types of DIMMs, DDR modulus, DDR modulus 2, rectangulars, DDR, that's DDR1, that's why. So generally the DIMMs follow, you use a more advanced, like load reduced DIMM is used in DDR4.
Yeah.
The advanced memory buffer is used in DDR3. The problem, as you mentioned, with advanced memory buffer is what in DDR3, why they couldn't use it in DDR4. Why is you couldn't use the same AMB in DDR4 that's used in DDR3? You said it when you were doing the presentation.
Sorry, can you repeat the question?
Huh?
Can you repeat the question?
Yeah, why can't we use the same advanced memory buffer that we used in DDR3 and DDR4? When you send the data in DDR3 through the AMB, how does it go out? You have to send the data in.
Yes. Bursts?
Serial.
Okay.
Remember you said that when we were doing your presentation. And when you do the load reduce, you send it in parallel, all
Yeah.
64 at one time.
Yes.
Right?
Only for fully buffered it is serial.
Yeah, there you go, fully buffered DIMM.
Yeah.
That doesn't work well for higher speeds.
Right. Yeah.
That's why they went to load reduced. We got a question, yay.
Can I ask something?
Sure.
We say that for the DDR4 we have a 64-bit bus, right?
Right. Yeah.
And why different DIMMs have a different number of pins? Why would we say we have 200 pins, let's say, when the
Yeah.
bus is 64?
No, that is between different DDR generations, not in. So here, right, in compared to different DDR generations, there are different number of pins here. But in the same generation, the pins are the same. The number of pins are the same. Is that what you meant?
Yes, somehow.
Uh,
But why it's 200? Why do we need 200 pins?
Not
That's
sure
what I was
actually.
trying to understand, but-
Yeah, I'm not sure
Oh,
about
we
that.
look at it.
Yeah, I'm not sure.
Oh wait, what's on the back of the part? Why is it called a dual inline memory module?
Oh, there are pins on both the sides.
Yeah, I know.
But why is it called a DIMM? What else is there on both sides?
DRAM chips?
Yeah.
Okay.
As compared to a SIM,
Okay.
where they're only on one side, right?
Okay.
All right, any other questions?
On the PCB tracing, the
Right.
purple PCB tracing,
Right.
that side of it. So you're trying to do the matching, right? So that's
Right.
gonna increase delay on the figure for the match, right?
Yeah, it does.
Okay, so is that's the only way to do it, is to increase delay for one of the signals? You can't speed up another signal?
Yeah, I mean, you have to, I mean, the longest trace, you cannot shorten the longest trace, right? So you have to make everything else longer, same as that.
Or is that really only whatever that's doing is making all the traces the same way?
Yeah, I mean, it makes the meandering pattern so that the lengths are the same, right? So
Top left one is not modified. That's the longest.
that's the longest one.
All right, any other questions? Let's thank our speaker.
Thank you.